What is the name of the compound below? A. E3-bromopent-2-ene. B. E3-bromopent-3-ene. C. Z3-bromopent-2-ene. Or D. Z3-bromopent-3-ene. So let's start by working out if it's E or Z. So on the left, the highest priority group is going to be this methyl group of CH3. And on the right, it's going to be bromine. If you have a halogen on your alkene chain, that's always going to be the highest priority group. So then we need to look at if it's 2 or 3. So it's going to be 2 because you want to have the double bond the fewest number of carbons away from the beginning. So that's going to be 1, 2 carbons away. So we know it's going to be a 2, so we can rule out B and D. So going back to whether it's E or Z, we know that they're on opposite sides of the double bond, these high priority groups. So that's going to make it E. So that's going to leave us with A, which we can then write in the answer box. So to get the mark for this question, you need to write A in the answer box provided. Which statement about bonds is correct? A. The C double bond C bond in ethene is more polar than the C single bond C bond in ethane. B. A sigma bond is stronger than a pi bond. C. The HCH bond angle in ethane is greater than the HCH bond angle in ethene. D. A sigma bond is formed from sideways overlap of p orbitals. So we need to work out which is correct. So the first one, the carbon-carbon double bond in ethene is more polar than the carbon-carbon single bond in ethane. This one is incorrect. Then B, the sigma bond is stronger than the pi bond. This one is correct, and that's because of the greater and stronger orbital overlap in a sigma bond versus a pi bond. So B is correct, but we need to check the other two. So the part C is asking about bond angles in ethane and ethene. So if we draw ethane and ethene, so starting with ethane, we have our carbon-carbon single bond and we have 6 hydrogens. So we can see that we've got 4 bonding pairs and no lone pairs, which makes it a tetrahedral structure with a bond angle of 109.5 degrees. Then if we draw ethene, we have our carbon-carbon double bond and we have 4 hydrogens. We can see we've got 3 bonding pairs and no lone pairs, which makes it trigonal planar, which is 120 degrees. So trigonal planar, 120 degrees is a lot bigger than 109.5 degrees. So the bond angle in ethene is greater, but that's not what this statement says. So this is incorrect. Then looking at D, the sigma bond is formed from sideways overlap of p orbitals. This is incorrect. This should read pi bond. And the sigma bond is formed with the direct head-on-head overlap of p orbitals rather than a sideways overlap. That's pi bonding with a sideways overlap. So D is incorrect. And then in the answer box, we can write B. So to get the mark for this question, you need to write B in the answer box provided. Which of these reagents will not react with HOCH2CH2CH2COOH? A. NaCN in ethanol. B. C2H5OH in the presence of an acid catalyst. C. CH3CO2O. Or D. Concentrated H2SO4. For this question, we're looking at the reagents that won't react with our compound. So looking at the functional groups first, we have an alcohol and a carboxylic acid. So we're looking with reagents that would react with an alcohol or a carboxylic acid, we can eliminate them. So starting at A. So A, we have NaCN in ethanol. So these are the reagents to turn a haloalkane into a nitrile. So looking at what we have as our functional groups, we don't have a haloalkane, so these reagents won't work. Then looking at B, so we have this alcohol group shown by the OH in the presence of an acid catalyst. These are the reagents and conditions for what's called esterification. Now, because we're given an alcohol, that means it's going to react with our carboxylic acid group. But it doesn't matter, because even if we had this being a carboxylic acid in the presence of an acid catalyst, this would be fine because we've got the alcohol as well, and a carboxylic acid and an alcohol react to form an ester. Then looking at C, this is what's called an acid anhydride. And what these do is they react with alcohols to form esters again. So an acid anhydride will form an ester with our alcohol. Then finally, looking at concentrated sulfuric acid, this will react with our alcohol to form an alkene. So all of this information can be found with the OCR reaction map. So if this question was a little bit difficult, then it's worth printing out this reaction map and trying to learn it. So the only reagents that don't react to form either an ester, an alkene, or anything else is A, because we don't have this haloalkane. So we write A in the answer box, and to get the mark, you need to write A in the answer box provided. Which compound can be refluxed with acidified potassium dichromate 6 to form an organic product with the molecular formula C5H8O2? And then we have 4 different compounds shown. So firstly, we're looking for groups that will react when refluxed with acidified potassium dichromate. And we must have the formula of C5H8O2. So looking at A first, this alcohol group won't react with acidified potassium dichromate under reflux because it's a tertiary alcohol. But this aldehyde group will, and it will produce a carboxylic acid under reflux. But we can see that this isn't matching the molecular formula because we've got 3 oxygens and we're only supposed to have 2. So we know that it can't be A. Then moving on to B. So we've got this alcohol group, which is a secondary alcohol. So that will react when refluxed with acidified potassium dichromate, and it will produce a ketone. So we get rid of this hydrogen and we form a carbon double bond oxygen. And then, similar to part A, well, this aldehyde group will react and we form a carboxylic acid. So again, we've got 3 oxygens, so it can't be B. Then looking at C, this alcohol group is a secondary alcohol, so it will form a ketone, and then we eliminate this hydrogen. It's got a ketone group already, and this ketone group won't react when refluxed with potassium dichromate. So we've got these 2 oxygens, then we need to count the carbons and the hydrogens. So we have 1, 2, 3, 4, 5 carbons, so it's looking promising. And then we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So C is looking like it's going to be our answer, but we just want to double check. So looking at D, we have this primary alcohol, and a primary alcohol, when refluxed with potassium dichromate, will form a carboxylic acid, and then we have this aldehyde group, so that will also form a carboxylic acid group. And then we can see we've got more than 2 oxygens, so it can't be D. So our answer is definitely C, which we can write in the answer box. And to get the mark for this question, you must write C in the answer box provided. Which structure shows a section of polypropene? And we're shown 4 different structures. So if we draw a repeating unit of polypropene, that's going to be the carbon-carbon double bond with the CH3 or the methyl group, hydrogen, hydrogen, and hydrogen. When it becomes a repeating unit, it loses this double bond, and then it will have these extended bonds where it's repeating from. So then if we try and match this to one of the structures we're shown, so we don't have a double bond in this unit. So this is going to be what's shown. And if we look at this, we're trying to compare it. There's no double bond in what we've drawn, so we eliminate anything with a double bond. And then if we look here, this has a side chain rather than it being a straight, flat 3-carbon chain. So it's not going to be C either. Instead, we're going to have the methyl groups coming up here, which is this bit on our repeating unit. So it's going to be D. And to get the mark for this question, you need to write D in the answer box provided. Which alcohol reacts with an acid catalyst to form a mixture of stereoisomers? A. 3-methyl-butan-2-ol. B. Pentan-1-ol. C. 2-methyl-hexan-2-ol. Or D. Heptan-4-ol. So when you react an alcohol with an acid catalyst, you get an alkene. So we're going to be looking for EZ isomerism. So if we start with drawing out A, so we've got butan-2-ol, so we need a 4-carbon chain, and then we have 3-methyl, so here, and then 2-ol, so our OH on carbon number 2. When we react with this acid catalyst and form an alkene, we can either form one here or here, and we get rid of this OH group. So if we look at this one, so that has 2 hydrogens, so we can't have EZ isomerism, so no EZ. And then here we have 2 CH3 groups again, so there's no higher priority, so there's no EZ stereoisomerism. So it can't be A, which we can eliminate. Then if we move on to look at B and we draw pentan-1-ol, so we've got a 5-carbon chain, and then we've got an alcohol on carbon number 1. So when we form a double bond, we can only form one, and it's going to be here. Then if we got rid of our OH when we form this alkene, we've got 2 hydrogens, so again we've got no high priority groups, so we have no EZ stereoisomerism, so it can't be B. Then if we look at C, we have 2-methyl-hexan-2-ol, so we need a 6-carbon chain. So here if we draw a 6-carbon chain, and then we need 2-methyl and hexan-2-ol, so that's going to be both on carbon number 2. Then when we form our alkene, we can form one here, here, and here, and we get rid of this alcohol group. So this first one, we have 2 hydrogens, so we can't have EZ isomerism. Also, on this second one, we have 2 hydrogens, so we can't have EZ isomerism. And then on number 3, we've got 2 CH3 groups, so there's no EZ stereoisomerism. So it can't be C. And finally, if we draw out D, that's heptan-4-ol. So we need a 7-carbon chain. So here we've drawn a 7-carbon chain, and we want an alcohol on carbon number 4, which would be here. And then if we draw its alkenes, we can either form one here or here, and then we will rub out this OH group. So if we look at the first one, we have a hydrogen here, so we're going to have a high priority group here, and then we have a hydrogen here, so this group is going to be our high priority group. So we do have EZ isomerism for group 1, so that's good. But we need a mixture of stereoisomers, so we need to look at number 2. So number 2 will have a hydrogen here and here, so it will have this is its high priority group and this is its high priority group. So again, we're going to have EZ isomerism. So that's really good because we've got this mixture of stereoisomers, and the key in this question was to realise that you form an alkene and the stereoisomers associated with alkenes are EZ stereoisomers. And the answer for this question is D, so to get the mark for this question you need to write D in the answer box provided. Which of the following reacts with ethanoic acid and with phenol? A. Aqueous potassium hydroxide. B. Bromine. C. Calcium carbonate. Or D. Methanol and an acid catalyst. So in this question, we have to react with ethanoic acid and phenol. So if we draw out both of these, we have a 2-carbon chain with a carboxylic acid group, and we have a benzene ring with an OH group attached. So for these questions, I'm going to draw the organic products of the reactions rather than the byproducts as well, because we're only really looking at the organic products here. So looking at A first, so that's aqueous potassium hydroxide. So it's going to form a carboxylate ion with ethanoic acid, where we have the double bond oxygen, but this OH becomes an O-, and then that can bond with the potassium positive ion from potassium hydroxide, so the K+. A similar thing will happen with phenol, where the O from the OH becomes O-, and then it bonds to the potassium ion. So A does react with both, so it's very likely that this is our answer. Then looking at B, so bromine. Bromine doesn't react with ethanoic acid, but it does react with phenol. And it will be tri-substituted if there's an excess of bromine, where it's substituted in the 2, 4, and 6 positions on the benzene ring. So here we've drawn our organic product for B, but it doesn't react with ethanoic acid, so it can't be our answer. Then looking at C. Calcium carbonate. So with acids, this reacts, and it's a test for acids. When you react them with a carbonate, you'll produce carbon dioxide, but you'll also produce an organic product. So like with A, we're going to have a carboxylate ion from our ethanoic acid, and we're going to use 2 of these and bond it to Ca2+, that's the calcium ion. But phenol is not a strong enough acid for this test to work, so it won't react and it won't produce an organic product here, but it will react with ethanoic acid. But because calcium carbonate doesn't react with both, it can't be our answer. Finally, if we look at D, so we have methanol and an acid catalyst. So methanol and an acid catalyst are the reagents for esterification, but you need a carboxylic acid, which can be found in ethanoic acid, where we have this ester group being formed here, where the double bonded oxygen is coming from the carboxylic acid and the single bonded oxygen is coming from the methanol. So here we've got our ester, but it doesn't react with phenol because phenol doesn't have a carboxylic acid group for it to form an ester. So D only reacts with ethanoic acid, so it can't be our answer. So therefore, to get the mark for this question, we need to write A in the answer box provided. Which isomer of C6H12O2 produces the smallest number of peaks in its carbon-13 NMR spectrum? We're given 4 isomers below. So we're looking for carbon-13 NMR peaks and the smallest number. So let's start by looking at how many carbon environments each of the isomers have. So if we look at A first, we have 1 because these 2 groups are the same environment. Then we've got 2, 3, 4, 5 carbon environments. So if 5 is the lowest number, then it's going to be A, but we don't know this for certain yet. Then looking at B, we have 1, 2, 3, 4, 5 again. So A and B can't be the smallest number because there's the same number in each. So it can't be either of these. Then we look at C. So we have 1, and we've got 3 1s because we've got 3 carbons with the same environment. Then 2, 3, 4. So C has 4. So it's likely this is going to be our answer because it's got the smaller number than 5. But if D has less than 4, then it's going to be D. But we need to check. So in D, we have 1, 2, 3, 4, 5 again. So it can't be D, and it's definitely C as our answer. So to get the mark for this question, you need to write C in the answer box provided. What is the structural formula of ethyl 3-methyl-butanoate? A. CH3, CH2, COO, CH2, CH2, CH, CH3, 2. B. CH3, CH2, COO, CH, CH3, CH2, CH3. C. CH3, CH2, CH, CH3, COO, CH2, CH3. Or D. CH3 brackets 2, CH, CH2, COO, CH2, CH3. So the 3-methylbutanoate, so the O8 means it's an ester, and the 3-methylbutanoate is going to come from the carboxylic acid of the ester. So if we draw out this carboxylic acid, we're going to have a 4-carbon chain, and then we're going to have our OH, our carboxylic acid group, and our 3-methyl group. So then when we form the ester, we get rid of this OH, and we're going to replace it with an oxygen from an alcohol, and then a carbon chain. So we have ethyl as our carbon chain, which is 2 carbons, so we need to draw 2 carbon chains. So then we need to match which of these is relevant to the structural formula. So if we look at the beginning, we have 2 CH3 groups, because this would be CH3 and this would be CH3. So we're starting with 2 CH3s, which is going to be D. So to get the mark for this question, you write D in the answer box provided. What is the number of alicyclic structural isomers of C5H10? A3, B4, C5, or D6? For this question, I'm going to start by drawing different structural isomers of C5H10. And then we're going to look at which ones are acyclic. So here is our first one where we've got a double bond, we've got 5 carbons and 10 hydrogens, but we could have the double bond at different points in this carbon chain, which I'm going to draw now. So we can also have it as like a side chain coming off, or we can just have a normal methyl group as a side chain and then the double bond in the longer chain. And finally, we could have it like this with the double bond at the end and a side chain. So these are the ones with a double bond. Now if we look at ones without a double bond, we need to make them cyclic, because otherwise we won't be able to have 10 hydrogens. So our first one is going to be cyclopentane, which is quite familiar, hopefully, from your A-level studies. Then we can have cyclobutane with a side chain, or cyclopropane with 2 side chains. But these 2 side chains could be at different points on the triangle, as shown here. And then we could have an ethyl group coming on the top or from any corner, but it would be the same. Then we need to look at which ones are acyclic. So alicyclic is when you have an all-carbon ring. And this carbon ring can be saturated or unsaturated, but it needs to be a carbon ring and it needs to be all carbon. So looking at these structural isomers we have, the only all-carbon rings are these 5 at the bottom. So these 5 are saturated because they are all alkanes and there are no double bonds. So there are 5 of them, so the answer for this question is going to be C. And to get the mark for this question, you need to write C in the answer box provided. Complete combustion of 1.00 grams of a hydrocarbon gives 3.38 grams carbon dioxide. What is the empirical formula of the hydrocarbon? A, CH, B, CH2, C, C2H5, or D, C3H8. So firstly with this question, let's highlight the key pieces of information. So that's the mass of the hydrocarbon and the mass of carbon dioxide. We don't need to highlight that it's complete combustion, because with complete combustion you form carbon dioxide, and with incomplete combustion you form carbon monoxide. But we're already told we're forming carbon dioxide, so we don't really need to worry about if it's complete or incomplete combustion in this question. And then we also need to highlight that we want the empirical formula. So if our answer is C2H2, we can simplify that to CH. for example. So we're going to be using an equation triangle in this question, and the equation triangle that we're going to be using is mass is equal to moles times the relative formula mass. So if we start by looking at carbon dioxide, that's going to be 3.38 divided by 12 plus 16 times 2. So that's the relative formula mass of carbon dioxide. And that equals 0.0768 moles of CO2. And then we can work out the relative formula mass of the hydrocarbon by using these moles. So we can do 1 divided by 0.0768, and that equals 13, which is the relative formula mass of the hydrocarbon. So now we need to look for something that has a relative formula mass of 13. So that's going to be 1 carbon, because carbon has a relative formula mass of 12, so we can only fit 1 in. And then if we did 13 minus 12, that equals 1. And the relative formula mass of hydrogen is 1, so that means we're going to have CH as our empirical formula, which is A. So to get the mark for this question, you need to write A in the answer box provided. What is the molecular formula of the steroid molecule below? A. C18H24O2. B. C18H26O2. C. C18H28O2. Or D. C18H30O2. So we need to look at in this question that the only thing that's changing in our multiple choice options is the number of hydrogens. So let's number our hydrogens in this steroid molecule. We have 1, we have 2, 3, 4 on the phenol side group, and then the rest of it is a cycloalkane. So we need to look for each carbon needs to have 4 bonds attached, and where it doesn't, we need to draw on the hydrogens. But these 2 carbons would have had a hydrogen, but because it's bonded to another carbon, and this is a phenol where you've got alternating double and single bonds, that means that these carbons aren't going to have any hydrogens attached, and this is a common point where students might trip up. But counting the remaining hydrogens, we have 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Then we've got 3 up here, so 16, 17, 18, 19, 20, 21, 22, 23, and then we'll have 1 here being 24, because then each carbon is going to have 4 bonds. And then if we've got 24 hydrogens, then that means our answer is going to be A. So to get the mark for this question, you need to write A in the answer box provided. Which statement or statements is or are correct for gas chromatography? 1. The components in a mixture can be identified from their retention time. 2. The relative peak areas give the proportions of components in a mixture. 3. Calibration curves are used to confirm the concentrations of components in a mixture. A. 1, 2 and 3. B. Only 1 and 2. C. Only 2 and 3. Or D. Only 1. So we're looking for which statements are correct. So if we start by looking at 1, the components in a mixture can be identified from their retention time. So this is true, and it's a similar principle to when you use thin layer chromatography and you work out their retention factor by working out how far the solvents travelled and how far the mixtures travelled. It's a similar thing with retention time. It's just in a gas chromatogram, retention time is how long the components are staying in the stationary phase versus the mobile phase, and that gives you their retention time. But it works on a similar principle, and it can give you the components. You can be able to identify them from the retention time. Then if we look at relative peak areas give the proportions of components in a mixture, This is also correct. So it might not be very clear when you get a gas chromatogram, because if you've got different peaks, then you might think that the highest peak is going to have the biggest area. That's not always the case, and working out these areas and integrating the peaks to get an area is how you work out the proportions of the components. It's often used in the drinks industry to work out how much alcohol is in different things, for example. Then, if you look at calibration curves are used to confirm the concentrations of components in a mixture. This is also true. And for example, you could plot the peak area against the percentage of ethanol if you wanted to work out how much the concentration was in this alcoholic beverage that you're testing, maybe in a manufacturing industry. So all three statements are correct, and so that's going to be A. To get the mark for this question, you need to write A in the answer box provided. Which of the following reactions produce propan-1-ol? 1. The alkaline hydrolysis of 1-chloropropane. 2. The acid hydrolysis of propylmethanoate. 3. The acid hydrolysis of propane nitrile. A. 1, 2 and 3. B. Only 1 and 2. C. Only 2 and 3. Or D. Only 1. So let's draw out propan-1-ol to begin with. So that's going to be a 3-carbon chain with an OH group on carbon number 1. So then if we look at the alkane hydrolysis of chloropropane, so drawing out chloropropane, so that's a 3-carbon chain with a Cl on carbon number 1. And then it's the alkaline hydrolysis, so that's with OH minus because that's the generic form of a base. And if we have a delta positive here and a delta negative here, this is going to be nucleophilic substitution, where the chlorine is substituted for this OH. And then we're going to form our propan-1-ol. So 1 is correct, and it does produce propan-1-ol. Then if we look at the acid hydrolysis of propylmethanoate, so drawing this out to begin with, we have our double bonded oxygen, or our carbonyl group, we have our oxygen, so our ester group, and then we've got our propyl chain. So acid hydrolysis is going to break this ester bond. You're going to form your alcohol and carboxylic acid back again. So you get your propan-1-ol and you'll get methanoic acid, which is here. But the only one we really care about is propan-1-ol, which is formed, so 2 is also one of the reactions that we need. Then we need to look at the acid hydrolysis of propane nitrile. So drawing out propane nitrile, we have our 3-carbon chain, and then we have an extended line where we've got our nitrile group attached. So this is in your reaction map and your reaction pathways, which if you struggle with this question, you should look back on and maybe make a revision guide from it. And when you do acid hydrolysis of a nitrile, you get a carboxylic acid. So we would get propanoic acid, which I can draw here. So again, this is not going to be propan-1-ol, this is going to be propanoic acid, which is not what we wanted to form. So it's not going to be 3. So it's just 1 and 2, and that's going to be B. So to get the mark for this question, you need to write B in the answer box provided. Which compound or compounds could be prepared by reacting benzene with an acyl chloride in the presence of a halogen carrier? We're given 3 different compounds, and we're told A is 1, 2 and 3, B is only 1 and 2, C is only 2 and 3, and D is only 1. So if we draw a generic structure of an acyl chloride, so here we have a chlorine, a carbonyl group, and an R group. So when you react with benzene in the presence of a halogen carrier, what happens is this chlorine drops off and it will bond to your benzene ring. So now we need to look at the different options. So what will happen is we'll have a CO being bonded. So we are looking for something that has CO. So it can't be number 1 because this has CH2 before you even get to your CO group. So it's not 1. And then if we look at 2, so 2 would mean that the R group becomes hydrogen. And then you get CHO as your side group that's just bonded to your benzene. So 2 is correct. Then looking at 3, 3 would mean that your R group in your acyl chloride is CH3. And that is possible, that's still going to be an acyl chloride, and you would form this in the presence of a halogen carrier with benzene. So 3 is also correct. Then we need to look at something that says only 2 and 3, which is going to be C. So to get the mark for this question, you need to write C in the answer box provided. The structure of hydrocarbon A is shown below. A. Hydrocarbon A can be reacted with bromine in the presence of ultraviolet radiation to prepare CH3 brackets 2, CCH, Br, CH3. What is the systematic name for CH3 brackets 3, CCH, Br, CH3? So firstly with this question, let's draw out the structure we need to name. So drawing this, we're going to add the bromine to carbon number 2. So we have our 3 methyl groups, our carbon chain, and then Br for bromine. Now we can start to name this. So we always start with the highest priority group, which is going to be bromine, and that's on carbon number 2, so we go 2-bromo. Then we look at the side chains. So we've got 2 on carbon number 3. We have 3,3-dimethyl. And finally, we need to look at the longest carbon chain. So that's going to be 1, 2, 3, 4 carbon lengths long, which is butane. So this is going to be our full systematic name for the structure, 2-bromo, 3,3-dimethylbutane. And you need to write this systematic name in order to get the mark for this question. B. CH3 brackets 3 C CH Br CH3 has stereoisomers. Part 1. Explain the term stereoisomers and name this type of stereoisomerism. So this question relies on recall. And if you got this question wrong, it's worth noting this on a flashcard so that you can revisit it and learn the set phrase to write. So the explanation that they want for what a stereoisomer is that there's the same structural formula but a different spatial arrangement of atoms. You could have also said a different arrangement of atoms in space. So to help us identify the type of stereoisomer in this compound, let's draw it out again. So we have our 2 side groups and the beginning of our carbon chain, our 4 carbon chain lengths, and then our bromine. So the type of stereoisomer here is an optical isomer because we have what's called a chiral carbon center, where we have 4 different functional groups attached to a carbon. So this type of stereoisomerism is called optical isomerism when you have a chiral carbon. So that's what we can put here. We can put optical for the type of stereoisomerism. And to get the mark for this question, you must have the correct explanation, which I've written here, and you must have said optical. You need both bits to get the mark. Part 2. Draw 3D diagrams for the stereoisomers of CH3 brackets 3 C CH Br CH3. So the key here is that they want 3D diagrams, which means we're going to need to use wedges. So drawing out our structure again, just so that we know where the chiral center is here, and then we can label our chiral center with an asterisk. So carbon has 4 groups attached to it. We have an invisible hydrogen here because in skeletal diagrams you don't draw on the hydrogens. But there are 4 different groups attached to this carbon. And because there are 4 groups in carbon, we're going to have tetrahedral wedges. So if I draw the dashed wedge here and then the solid wedge, we'll have bromine on the top, our methyl side groups here, where we have CH3 and 3 of them. Then we're going to have our hydrogen and our CH3. So as we can see, this big methyl side group is this component of our 4 groups. Then we have our bromine, we have our hydrogen, and then this is going to be CH3, which we've written. Then, because it's optical isomerism, we have a mirror image, and that's going to be our other stereoisomer. So we have the same layout, but our wedges flip. So instead, our dashed and our solid wedge are going to be on the left. But we have the same groups attached, so we have the CH3, the hydrogen, the bromine, and then our CH3 also attached. So these are our 2 different stereoisomers for our compound that we've been given. And to get the mark for this question, you need to have both 3D diagrams. If you've only drawn one, that's going to be 1 mark. To get 2 marks, you need to draw both of them. C. Complete the table to show the mechanism for the reaction of hydrocarbon A with Br2 to form CH3 brackets 3C CH Br CH3. Use skeletal formulae for all organic compounds. Use dots to show the position of unpaired electrons. So this question is using a mechanism called free radical substitution. So a common example of free radical substitution would be using chlorine. In this case, we're using bromine, but you might have seen this done with chlorine in class. Now, at the end of this, we're supposed to form this product. So we need to double check that we've done it right if we do form this product. So free radical substitution consists of 3 steps or 3 stages: initiation, propagation, and termination. Here we're only asked to show initiation and propagation. So initiation is when you form your radicals. So you'd start with your bromine, and then under UV you form 2 bromine radicals. So you could write UV on the arrow here. That's not going to do you any harm in this question, and it is how you form the radicals. You need this ultraviolet light to form them. Then with propagation, you start by adding a bromine radical, and then you get hydrogen bromide, but then you'll get a radical of your hydrocarbon. So you'll have the radical where you want to add your bromine at the end, because in the next stage you take this radical and then you're going to add Br2. So the bromine can then be added to where your radical part is on your hydrocarbon, and then you can get the product that you wanted at the end, where you've got your bromine on carbon number 2, and then you're left over with a bromine radical. So here are the initiation and propagation steps. Termination, all it is when you add 2 radicals together. So that could be 2 bromine radicals and you'd form bromine again. You could form a bromine and this radical, so you would form your product again. Or you can take 2 of these hydrocarbon radicals and then you just make a very long hydrocarbon chain. But that's all that termination is. But this question does not ask you for termination, only initiation and propagation. To get the 3 marks for this question, you get a mark for your initiation step, and then you get a mark for each line or each equation in your propagation step. D. State 2 limitations of using radical substitution in organic synthesis. So our first limitation of radical substitution is that you can have further substitutions, and you keep substituting on your hydrocarbon chain until all the hydrogens are replaced with a halogen. Also, your second limitation is that the substitution could happen at different positions along the chain, so you might not always get the product that you want coming off at the end. So instead of saying further substitutions as the first limitation, the mark scheme would have also accepted saying produces different termination products, or more than one termination step, or a mixture of products are formed. So either of these 4 statements would have gotten you the first mark, Then your second mark, you have to say substitution at different positions along chain. Compounds B and C shown below are unsaturated hydrocarbons containing 9 carbon atoms. Part A. Compound B reacts with chlorine at room temperature, but compound C requires the presence of a halogen carrier. In both reactions, the organic compound reacts with chlorine in a 1:1 molar ratio. Part 1. Draw the structures of the organic product of each reaction. So, firstly, the difference between B and C when they react with chlorine is B can react at room temperature, but C needs a halogen carrier. And that's because of the different functional groups in the two compounds. So B has an alkene group, so a carbon-carbon double bond. And that means when it reacts with chlorine at room temperature, it's going to undergo electrophilic addition. But compound C has this benzene ring, and so it needs a halogen carrier because it's going to undergo electrophilic substitution. So if we draw the products of B and C, so if we draw B first, so most of B is going to remain the same, except this carbon-carbon double bond is going to be replaced with 2 chlorines. Then if we look at C, so what we're doing on compound C is we're substituting one of the hydrogens for a chlorine. So here we can add our chlorine, but the rest of C is staying the same. So you can see what electrophilic addition versus substitution looks like, because addition, you're adding these chlorines, so you don't need a double bond, but with substitution, you're replacing a hydrogen. So to get the 2 marks for this question, you get a mark for each organic product that's correct. Part 2. Explain the relative resistance to chlorination of compound C compared with compound B. So, as discussed in the last part of the question, the difference in the relative resistance to chlorination is due to the double bond versus the benzene ring. So if we break this down into reasoning, or scientific and chemical reasoning, so in B, the electrons, or the pi bond, which is the carbon-carbon double bond, is localized. So the electrons are localized and the pi bond is localized. But in C, the electrons, or the pi ring system, is delocalized. And this is going to mean that B has a higher electron density. So the electrons are very densely packed in this double bond, whereas in the benzene ring, they are more spread out. The electron density is lower. With a higher electron density, that means you're more susceptible to electrophilic attack. So to get the 3 marks for this question, so you get a mark for saying that the B electrons are localized or that the pi bond is localized. Here I've written a slash to indicate you can either say electrons or pi bond. Then you get your second mark from saying in C the electrons are delocalized or the pi ring system is delocalized. So again I've written a slash to show you can write either. Then you get your third mark for saying that in B the electron density is higher and that B is more susceptible to electrophilic attack. But you don't need to say more susceptible to electrophilic attack. They will also accept that B accepts the electrophile more, or B polarizes the electrophile more. And instead of saying the electrophile, you can write chlorine. They will allow that. Part 3. Outline the mechanism for the reaction of compound C with chlorine. Show the role of the halogen carrier. As I said in part 1, this mechanism that we're dealing with compound C is electrophilic substitution, where we substitute one of the hydrogens on the benzene ring with a chlorine. So the key in this question is that we need to show the role of the halogen carrier. So we need to start with how the halogen carrier helps us form an electrophile. So an example of a halogen carrier could be aluminium chloride, so AlCl3. And then we're going to add chlorine and produce a Cl+, that is going to be our electrophile. And then we also produce AlCl4-, which we're going to come back to at the end when we show how the halogen carrier can be reformed. So if we start by drawing compound C as our starting material, and then we're going to show how it initially reacts with the electrophile. So that's going to be Cl+. So what happens is the ring is going to be attracted to this electrophile, and we're going to produce an intermediate. So the mark scheme is pretty picky when it comes to how you draw the intermediate. So this curly arrow needs to be exactly on the points here on the dotted line. So it can't go above the dotted line, and it needs to meet the corners of this hexagon. Then we draw the side products on of the methyl groups, and wherever you want your chlorine to be added, you need to draw your hydrogen that you're going to substitute and then your chlorine. So you can do it anywhere on compound C because you're going to get the same product at the end. But if one of your groups had a directing effect, for example, then you would have to put it on a specific hydrogen or a specific carbon, and a specific hydrogen would be replaced. But because you're going to get the same product here, it doesn't matter where you're going to add your chlorine. Then we're going to draw an arrow of the hydrogen being attracted back into the intermediate so that we can substitute it and produce our product. So we're going to have our benzene ring reformed, our side groups stay the same, and then our chlorine is going to be added with our H+ that's been substituted. Now, this H+ is going to be added to our AlCl4 that we formed at the beginning, and we can reform our halogen carrier, so AlCl3, and then we're left with hydrogen chloride. So this is electrophilic substitution. It's a very common example, and if you did struggle with this question, it's worth maybe having this as an example and then playing around with different compounds and different halogens and halogen carriers, because it's a really good mechanism to have in your back pocket for these exams. To get the 5 marks for this question, you get a mark for generating your electrophile, you get a mark for attacking your Cl+, so the first step of this mechanism, you get a mark for your intermediate, and then you get a mark for the curly arrow coming from the carbon-hydrogen bond and reforming the pi ring. And then you get your 5th and final mark from showing the regeneration of your catalyst, which we've done right at the bottom here. Part B. Compound C can be prepared by trimerization of propanone, using concentrated sulfuric acid as a catalyst. Suggest an equation for this reaction using molecular formulae. So the key bits of this question are that we're preparing compound C through trimerization of propanone, and we need to show the molecular formulae in the equation. We don't need to write sulfuric acid in our equation because it's a catalyst, so we'd write it at the beginning and the end. So it's not changing and it's not going to be relevant in our equation. You could write it over the arrow if you wanted to, but the mark scheme does not require this. So firstly, let's look at propanone. So that's going to be a 3-carbon chain with a ketone group on carbon number 2. So working out its molecular formulae, that's going to be 1, 2, 3 carbons, so C3, and then 6 hydrogens, so H6 and then an oxygen. So the way we've worked out the hydrogens is each carbon must have 4 bonds. So it's got 1 bond going to this other carbon here, but it needs 3 more. So it's got these 3 lines of hydrogen, hydrogen, hydrogen. So then if we look at C, well, we know in the question it's got 9 carbons. So we don't need to worry about counting the number of carbons because we know it's got 9. So C9, but we need to work out how many hydrogens it's got. So again, we've got 3, 3, and 3, so 9 so far. But then we've also got 1, 1, 1, so 3 singular hydrogens. And that's because we've got these alternating double and single bonds in our benzene ring. and that means that you're going to have a group that's going to be able at each. But here we've got a methyl group, here and here, so the remaining gaps are going to be hydrogens. So counting these all, we have H12. So we can begin to construct our equation. We have C3H6O, and that's going to produce C9H12. We're also going to form water as a byproduct. And if you are unsure about why, you can look at propanone and see that it's got this oxygen group. And compound C doesn't have any oxygens. And a very common byproduct when it comes to polymerization is water. So now we need to balance the equation. So we need 9 carbons, so that means we need 3 propanones. And if we multiply by 3, that means we're going to have 3 oxygens, so we need 3 waters. And adding these 2 3s is going to balance out our hydrogens. So to get the 3 marks for this question, so you get a mark for the molecular formulae, you get a mark for having water as a byproduct, and then you get your final mark for balancing the equation.
Part C. An organic chemist is investigating compound D for possible use as a medicine. The chemist proposes a synthesis of compound D from compound C. Part 1. Predict the number of peaks in the carbon-13 NMR spectra of compounds C and D.
So the key thing in this question is that it's the carbon-13 NMR spectra that we're trying to look at. And whenever you're looking at spectras and you're trying to work out the number of peaks, the first thing you need to do is look at symmetry. So if we start with compound C, we have a line of symmetry here, we have a line of symmetry here, and we have a line of symmetry here. So 3 lines of symmetry. Then if we try and work out the peaks, so we only need to look at one little section here. So it's going to be this little bit of the pie. So we got 1, 2, 3 carbon environments here. And then if we go around the rest of the compound, we have 2, 1, 3, 2, 1, and 3. So you can see there's 3 3s, 3 2s, and 3 1s. So it's going in accordance with our 3 lines of symmetry. So then if we work out and we look at number of peaks, we've got 3, so we can write this in the table. Under compound C, we can put 3. Then if we look at compound D, so if we look at its side group first, we have 1, 2 carbon environments. But then moving on to the benzene ring, we have 3, 4, but we've got 2 4s because we've got this line of symmetry here. So 4, 4, 5, 5, 6, 7, and then we've got 8 and 8 because these 2 methyl groups are going to be the same carbon environment. So we have 8 carbon environments, so 8 peaks for compound D. To get the 2 marks for this question, you get 1 mark for 3 and then 1 mark for 8. Part 2. The chemist develops a 3-stage synthesis of compound D from compound C. Complete the flowchart and show structures for organic compounds. So this question relies heavily on your use of the reaction pathway map. So if you struggled with this question, I would look back at this reaction pathway map and try and learn it, or make a revision resource to try and learn it. So the first bit of this question is that tin and hydrochloric acid are very commonly used to go from a nitro group to an NH2 group, or an amine group. So that means we're going to have to form a nitro group from compound C. So if we draw out what we think the product should be, so we're going to have everything mostly the same, except we've got this NO2 group here, or on any of the 3 carbons. And the reagents for this is you have nitric acid, so HNO3, and then your catalyst is going to be sulfuric acid. So this is another example of electrophilic substitution, which we've covered in a previous bit of this question. But if you wanted more practice, you could use this as your example. So then when you add your tin and your hydrochloric acid, you're going to form your amine. So the NO3 is going to reduce and you're going to form NH2. Then we're trying to go and form this amide. So on your flowchart, the reaction for going from an amine or a primary amine to a secondary amide is when you add an acyl chloride. So that's going to be CH3COCl, because your acyl chloride has to have a CH3 group here, and then your CO and then your Cl would have been here, but you replace it and you form hydrochloric acid. So one of the hydrogens from the NH2 and then your chlorine from the acyl chloride form hydrochloric acid in this reaction. So to get the 5 marks for this question, you get a mark for each of your products, and then you get a mark for your reagent of nitric acid, you get a mark for saying sulfuric acid as your catalyst, and you get a mark for your acyl chloride as your reagent in step 3.
Alcohols can be used to prepare organic compounds with different functional groups. Part A. HOCH24OH can be oxidized to form HOOCCH22COOH. Part 1. State the reagents and conditions and write an equation for this oxidation. In the equation, use O for the oxidizing agent. So if we start with the reagents and conditions, the first thing we need is an oxidizing agent. So if you look on your reaction map for this syllabus, and you look at the reaction going from an alcohol to a carboxylic acid, you'll see an example of an oxidizing agent, which is potassium dichromate, so K2Cr2O7. But you also need it acidified, so you can write this as H+ or acid, and we need reflux. So this is so that it forms a carboxylic acid and not an aldehyde. If you wanted to form an aldehyde, you could distill with an oxidizing agent in acidic conditions. Now we need to look at the equation. So if we start with our reagents, we have HOCH24OH plus some oxidizing agent, and it's going to produce HOOCCH2 brackets 2 COOH. So going from an alcohol to a carboxylic acid, this is a condensation reaction. So we form water. Now we need to look at what's changed in the two reaction and products. So if we look at the carbons, it might seem like we've got different numbers of carbons because we've got 4 here, but we've got 2 here. But this 2 is not including this carbon and this carbon. So we still have 4 carbons. But our number of hydrogens has changed. And so to balance it with this H2O, we actually need 2 waters to make sure this is a balanced reaction. And looking at the differences in the oxygens, well, we have an additional 2 oxygens here, but we also have 2 from the water. So to balance, we need 4 oxidizing agents. So in this question, you get your 3 marks, your first mark coming from your reagents and conditions, your second mark coming from writing the oxidizing agent as brackets O, and writing water, so that gets you your second mark. And then your third mark comes from correctly balancing the equation. Part 2. HOOCCH22COOH is soluble in water. Explain using a labelled diagram why HOOCCH22COOH is soluble in water. So to answer this question, let's start by drawing out our carboxylic acid or our dicarboxylic acid. So drawing this out, we have our double bond oxygen, our OH group, then we have our CH2 brackets 2, and then our carbon double bond oxygen and our OH. So if something is soluble in water, this means that it's going to react with water and it can bond with water.
the most common bonds with water are going to be hydrogen bonds. So a hydrogen bond, if we had with water, we can have the lone pair on the oxygen of the H2O, our two hydrogens, a negative dipole on the oxygen, and a positive dipole on the hydrogen. You also need to label that this is a hydrogen bond. Alternatively, you could have had your hydrogen bond from the lone pair on the OH of your dicarboxylic acid, and it would bond to the hydrogen of H2O. And you could draw it like this, but you need to make sure that you're labeling this as a hydrogen bond. So to get the 2 marks for this question, you get a mark for the correct dipoles. So on this alternative one, the dipoles, you'd have a negative dipole here and a positive dipole here on the hydrogen. So you get a mark for your dipoles, and then you get your second mark from making sure that it's going from the lone pair on oxygen to a hydrogen and that you've labelled it as a hydrogen bond. That gets you your second mark. Part B. HOOC CH2 COOH and HO CH2 4OH react together to form polymer E. Part 1. Draw one repeat unit of polymer E. The functional groups should be clearly displayed. So to start this, we need to draw out our dicarboxylic acid and our diol, and look at what groups are going to be lost and what bonds are going to be formed. So drawing out our dicarboxylic acid, we have our OH group, and then this is connected to a carbon, double bond oxygen. We have our CH2 group that's times by 2, and then we have our C double bond O, and then another OH. So then we're reacting with this diol, so we have our OH, and then we've got CH2 brackets 4 and our OH again. So what's actually formed is we have a carboxylic acid and an alcohol, and this forms an ester. So we get rid of this hydrogen, and this OH group at the end. So we have this ester bond in the middle, and it's all connected, and we've got a repeating chain, which is shown by these dotted lines. So we're only asked to show one repeat unit, and our repeat unit is going to have this ester bond in. If we were asked to draw 2, it would have 2 ester bonds in. And we've clearly shown our functional groups. So this is polymer E. It's an ester polymer, and it's a condensation polymerization, which means you would form water, but we're not asked to write an equation, so we don't need to worry about water at the moment. To get the 2 marks for this question, you get a mark for the ester link, and then you get a mark for the rest of the structure being correct. Part 2. Governments are encouraging the development of biodegradable polymers to reduce dependency on persistent plastic waste derived from fossil fuels. Polymer E is a biodegradable polymer. Suggest why polymer E is able to biodegrade. So, as we already discovered in part 1, polymer E has an ester group. And this ester group can be broken down, which is why it's able to biodegrade, because it can be broken down via hydrolysis. To get the mark for this question, you need to write this statement. Ester group can be broken down via hydrolysis. Part 3. A large yield of polymer E can be obtained by reacting a diacyl dichloride with HOCH2,4OH. The diacyl dichloride is prepared from HOOC CH2,2COOH. Complete the equation for the formation of a diacyl dichloride from HOOC CH2,2COOH. So this question is relying on your knowledge of your chemistry reaction map. So if you found this question hard, I'd recommend going back, revisiting and trying to learn it. So the reagent that you need from going from a carboxylic acid to an acyl chloride is SOCl2. And because we're making a diacyl dichloride, that means we need 2 of these. So an acyl chloride has a double bond carbon and then a Cl. So what happens when you go from a carboxylic acid to an acyl chloride is the OH is replaced with a Cl or a chlorine. But the rest of the structure stays the same. So you have your CH2, 2, and then again your second bit to make it the diacyl dichloride. You need to replace your other OH with a chlorine. And then balancing the equation, you get sulfur dioxide and you get 2. And you also get hydrogen chloride. And you get 2 of these because you've lost your 2 H's in your OH. And you've got your excess chlorines from when you doubled your SOCl2. So to get the 3 marks for this question, you get a mark for writing SOCl2 as your reagent. You get a mark for the correct structure of your diacyl dichloride, and then you get your third and final mark for correctly balancing the rest of the equation. The carbonyl compounds F and G shown below contribute to the flavour of coffee. Part A. Compound F is a member of a homologous series. Part 1. Explain the term homologous series. So a homologous series will have the same functional group. So this would get you your first mark. Alternatively, you could say that it has similar chemical properties or reactions. Either one of these statements would get you the first mark for this question. And then we need to look at what makes them different in the series, and that's the fact that each member, or each successive or subsequent member, differs by CH2. The word successive or subsequent is key in this question, and the mark scheme has it in bold, so it's really important that you write it in your answer for this question. And then to get the 2 marks for this question, you get a mark for this first statement, so either same functional group or similar chemical properties / reactions. So either of those, that's your first mark, and then your second mark from saying each successive or subsequent member differs by CH2. Part 2. Predict the molecular formula for the member of this homologous series containing 24 carbon atoms. So, as we're told in part 1, F is a homologous series. So we're going to be looking at F and trying to work out its molecular formula when we have 24 carbon atoms. So the only bit in a homologous series that's going to differ is this CH2 group. We can expand it by adding more CH2s. So writing out what's not going to change, we have C4H8O. So that's just all of this excess here, because this group won't change and this aldehyde functional group won't change. We've got to have the aldehyde to make it homologous, and we have to have these 2 methyl side chains. So it's just going to be this middle CH2 that we're going to change. And if we look at what we're going to keep the same, we have 4 carbons, but we need 20. So we're going to do CH2 times by 20, so we get C20H40, and then we just add it to what we're keeping the same. So our molecular formula when we have 24 carbon atoms is going to be C24H48 and then an oxygen. To get the mark for this question, you need to write C24H48O. Part B. Describe suitable chemical tests with observations that would confirm the presence of the functional groups in F and G. So the first thing we need to do with this question is identify the functional groups in F and G. So if we start with F, the functional group in F is this aldehyde group. So F/aldehyde, and the test for an aldehyde is going to be Tollens reagent. So we write Tollens and the positive test that we would get with the aldehyde, which is a silver mirror. Then we need to look at the functional groups in G. So G has 2 functional groups. It has a ketone here and an alkene here. So if we start with the alkene, so G/the alkene, because that's the functional group we're going to look at first, The test for the alkene is bromine water, and the positive test with the alkene present is going to be discoloration, or it's going to go colourless. And then we can look at G/ the ketone. So the test for a ketone is 2,4-DNP. And if there's a ketone present, there'll be an orange precipitate formed. The alternative test to confirm that we've got G and not F is if we reacted G with toluenes, we wouldn't get a silver mirror, because 2,4-DNP is a test for a carbonyl group. So it would react with F and form an orange precipitate, but F with toluenes would form a silver mirror and G won't form a silver mirror. So to get the 4 marks for this question, you get a mark for your aldehyde test, a mark for your alkene test, and then you get a mark for each ketone test. Part C. Compound F reacts with HCN using NaCN and H+. Part 1. Outline the mechanism for the reaction of F with NaCN and H+, and state the name of the mechanism. The structure of F has been provided. Include relevant dipoles, lone pairs, and the structure of the organic product. So the first thing to do whenever you're given a mechanism question is to check the dipoles and put them on your reactant. So we're going to have a positive dipole on the carbon and a negative dipole on the oxygen of the carbonyl group. And then we have our CN- that we get from our NaCN. And this negative CN, or this nucleophile, is going to be attracted to the positive carbon. And then we're going to form an intermediate. So keeping everything else the same, so we have CH, CH3, CH3, CH2, because a lot of the time people get tripped up by messing up the first bit of the reactant. So it's making sure that you've got this completely correct and the same. And then we have C and a hydrogen. We have a singularly bonded oxygen now with a negative charge and lone pair. And we'll have our CN bonded to this carbon. Now we react with our next reagent, which is H+. So H+, and this lone pair on the oxygen is going to be attracted to the H+, and we're going to form our organic product. So again, keeping everything the same, so our CH, CH3, CH3, CH2, and then we have a hydroxynitrile, so CH, OH, and CN. So this is our organic product, and now we need to identify or name the mechanism. So the name of this mechanism, we have a nucleophile, so we can start by writing nucleophilic, and then you've got 2 choices, addition or substitution. Well, we haven't substituted anything in compound F, so we are adding. We've added this CN, we've added this nitrile, so it's nucleophilic addition. And to get the 5 marks for this question, you get your first mark from your curly arrow going from the CN- nucleophile or the nitrile nucleophile. You get your second mark for your dipoles being correct on the carbonyl functional group. You get your third mark for your second curly arrow, so going from the lone pair on oxygen to the H+. You get your 4th mark for having the correct organic product, so this hydroxynitrile. And then you get your 5th mark for correctly naming the mechanism. Part 2. Explain why the mechanism in C Part 1 involves heterolytic fission. So the first mark in this question comes from defining the word heterolytic. Heterolytic means that one bonded atom will receive both electrons, or 2 electrons in this case. Then your second mark comes from defining the word fission. So fission is the breaking of a covalent bond. So this is how the 2 marks are awarded, one for defining heterolytic and one for defining fission. Cyclopentanol can be reacted to form cyclopentene.
Cyclopentene is a liquid with a boiling point of 44 degrees Celsius and a density of 0.74 grams per centimetre cubed. A student plans to prepare 4.00 grams of cyclopentene by reacting cyclopentanol with a boiling point of 140 degrees Celsius with an acid catalyst. The expected percentage yield of cyclopentene is 64.0%. The method used is that the student carries out the preparation using the apparatus set up for distillation as shown below. 1. The reaction mixture is gently heated and a distillate containing impure cyclopentene is collected. 2. The distillate has an aqueous layer and an organic layer. The student purifies the cyclopentene from the distillate. Part A. Calculate the mass of cyclopentanol that the student should use and explain how pure cyclopentene could be obtained from the distillate. So, firstly answering the first part of the question, which is calculating the mass of cyclopentanol. So in order to do this, we need an equation triangle, and the equation triangle we're going to use is mass divided by moles times RFM, or that mass is equal to moles times relative formula mass. So the first thing we're going to do is do 4 divided by 68. So what this is it's the 4 grams of cyclopentene, and then it's the relative formula mass of cyclopentene. So if we calculate it, that's 1, 2, 3, 4, 5 carbons, so C5, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, so that's equal to 12 times 5 plus 8, which equals 68. So these are going to be the moles of cyclopentene, and it equals 0.0588 moles of cyclopentene. So we can write that next to it just so that we don't lose track later on in the question. The next key piece of information we're going to use to work out the mass of cyclopentanol is the expected percentage yield of cyclopentene. So what we're going to do is 0.0588 multiplied by 100 divided by 64, which equals 0.0919 moles. And this will be of cyclopentanol. So you might have thought that the fraction should go the other way round, but actually that's going to give you a smaller moles. And because the percentage yield is less than 100, that means you're going to need more cyclopentanol in order to make 64% cyclopentene, because some of this percentage is going to be water. Then we need to work out the mass of cyclopentanol. So again, using the equation triangle, we do moles, so 0.0919, and then multiply by its relative formula mass, which is going to be 86. So again, we can work this out. We've got 1, 2, 3, 4, 5 carbons, so C5. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and we have an oxygen. So that's going to be 12 times 5 plus 10 plus 16, which equals 86. And working out the mass, that's going to be 7.90 grams. So it's really important that you've got the mass written to 2 decimal places as well in this question. Then looking at the purification techniques. Firstly, you need to add a neutralizing agent, such as Na2CO3 or sodium carbonate. Then we need to talk about the different layers in the separating funnel. So the organic layer is going to be on the top, and the organic layer is going to contain the cyclopentene. And that's because it's going to be less dense than the concentrated phosphoric acid. Then we need to dry with an anhydrous salt, to dry the organic layer with an anhydrous salt. So that's magnesium sulfate, sodium sulfate, or calcium chloride. Finally, we need to redistill at approximately 44 degrees Celsius, and this is because that's the boiling point of cyclopentene, which we're told in the question.
Part B. The organic layer in the distillate was analysed by IR spectroscopy. The IR spectrum is shown below. Explain how the IR spectrum of the organic layer suggests that cyclopentene has been formed and that the reaction is incomplete. So the key part of this question is that the reaction is incomplete and that we're trying to form cyclopentene. So if it's incomplete, that means we're going to have some cyclopentanol left. And we can see on the IR spectrum, we've got this smooth curve peak, which is our OH peak. So this is probably the easiest peak to identify because it is this smooth curve and all the other peaks are going to be jaggedy. So then we need to write our first statement. So the OH, or the alcohol peak, so naming the functional group is sometimes a good idea, just so that it's easier to check back you've definitely answered the question. And then we need to state what region it's in. So we've identified it with the arrow, but just to confirm, we need to say what wave number region. So that's going to be 3,200 to 3,600 centimeters to the -1. Then, because we're trying to form cyclopentene and it's incomplete, but we are going to form some, even though the reaction is incomplete. And looking at the datasheet, you can see the rough region of the OH peak and the alkene peak. The alkene peak is slightly harder to identify because it isn't just a smooth curve. You do need to look at the wave number region in your data book as well. But it's going to be this peak here. This is going to be your alkene or your carbon double bonded carbon peak. So if we start to write our second statement, we have our C double bond C, or our alkene peak. And the region that it's in is going to be the region of 1,620 and 1,680 centimeters to the -1. To get the 2 marks for this question, you get a mark for your statement about the alcohol peak, and then you get a mark for your statement about the alkene peak. This question is about organic compounds containing nitrogen. Part A. Salt H, CH3, 2, CH, NH3, Cl is used in the manufacture of garden weed killers. The flowchart shows the synthesis of the salt H from propanone. Complete the flowchart and show the structures for organic compounds. So let's start by drawing propanone. We have a 3-carbon backbone, and then we have CH3 as our 2 R groups and a double bonded oxygen, so a carbonyl group. When you react propanone with NaBH4, this is a reducing agent and it's going to undergo nucleophilic addition. So that's when this carbonyl group is turned into an alcohol group. So if we draw this structure out, we have CH, we still have our CH3R groups, but then instead of this carbon-oxygen double bond, we have an OH group. Then we need to look at the reagent of going from this alcohol group to a bromine. So this is nucleophilic substitution. And your reagents are NaBr or just Br-, so that's your nucleophile. And then you need H2SO4 or an acid to help with this nucleophilic substitution. The acid acts as your catalyst. Then we need to look at the next step. So we don't have any clues, but we do have this final salt product. So firstly, before we get to this salt product, we're going to have an amine formed. So that's going to be CH, NH2, and then we have our 2 CH3R groups. So the reagent to go from this haloalkane to an amine is NH3 and ethanol. Alternatively, you could have said that you're going to use an excess of NH3 or ammonia. Then finally, we need to look at the reagent to go from this amine to the salt. So we look at what we're missing. Well, we're missing a hydrogen and a chlorine. So our reagent is going to be hydrogen chloride.
To get the 5 marks for this question, you get a mark for each reagent that you've written, and then you get your other 2 marks from the 2 structures that you draw.
Part B. Aspartame, shown below, is an artificial sweetener commonly used as a sugar substitute. Part 1. Aspartame contains several functional groups. Apart from the benzene ring, name the functional groups in aspartame. So if we start working from left to right, our first functional group is here. And this is an ester functional group, which we can bullet point in this question. Then moving along, we have this amide functional group. So in the question, you don't get marks for classifying if it's primary, secondary or tertiary, but just for consolidation, this is a secondary amide. It would be a primary amide if you had NH2 here, and it would be a tertiary amide if you didn't have a hydrogen here. Then if we move along, we have this NH2 here, and that's an amine. So an amine means it doesn't have a carbonyl group, so it doesn't have this carbon double bonded oxygen. And this is a primary amine. So to make it secondary or tertiary, you need to get rid of these hydrogens. Then if we look at the last functional group here, we have a carboxylic acid. So the way marks are awarded for this question, it's not 1 mark per functional group correct. Instead, 4 groups correct will get you 3 marks. If you've got 3 groups correct, you get 2 marks. And if you've got 2 groups correct, you get 1 mark. Part 2. A sample of aspartame is hydrolyzed with aqueous acid. Draw the structures of the 3 organic products of the complete acid hydrolysis of aspartame.
So acid hydrolysis is when you're going to react with H+ and break some bonds. So the bonds that are going to be broken are this ester bond and this amide bond. So when you break your ester bond, you're going to form an alcohol and a carboxylic acid. And when you break an amide bond, you form an amine and a carboxylic acid. So starting with the ester group first, breaking it and forming the alcohol, we're going to form methanol. So CH3OH is our first structure. Then if we draw the carboxylic acid and the amine, so we're going to have our benzene ring at the bottom, and then the rest of the structure is the same except we're going to have NH2 and then our carboxylic acid. So making sure everything's the same by drawing the ring in the benzene ring. But because this is acid hydrolysis and you're going to have an excess of H+, what's going to happen is the NH2 is going to be converted into NH3+. Then we need to draw our last structure, so we're turning this into a carboxylic acid at both ends. So we're going to have HOOC, and then our carbon backbone, COOH, and our NH2. But again, because we've got this excess of H+, this NH2 is going to turn into NH3+. And to get the 4 marks for this question, you get your marks for each of the structures, so 1 for each structure, and then your 4th mark comes from remembering that the NH2 groups are going to be converted into NH3+ groups.
Part 3. Some people are concerned that aspartame C14H18N2O5 may have adverse health effects. Research shows that the safe maximum daily intake of aspartame is 1.7 times 10 to the negative 4 moles per kilogram. A typical UK adult has a mass of 75 kilograms. A can of a diet drink contains 167 milligrams of aspartame. How many cans of this diet drink is it safe for a typical adult to drink in one day?
So firstly, let's highlight the key pieces of information in this question. So that's going to be the molecular formula of aspartame. That's going to be the maximum daily intake of moles per kilogram, the average mass of an adult, and the milligrams of aspartame that a can contains. So the first equation triangle and the only equation triangle we're going to use in this question is mass is equal to moles times relative formula mass. So we're going to have mass at the top, moles, and then relative formula mass. So working out the relative formula mass of aspartame, that's going to be 14 times 12 plus 18 plus 2 times 14 plus 5 times 16, which equals 294 grams per mole. So now we're going to use this equation triangle to work out the moles in 1 can. So the way we're going to work this out is milligrams divided by relative formula mass will give us moles. So 0.167, so that's milligrams divided by 1,000 to get grams. And then we're going to divide by 294, and that equals 5.68 times 10 to the negative 4 moles in 1 can. Now we need to work out the number of moles per day. So that's going to be 1.7 times 10 to the negative 4 multiplied by 75. So that's using the units of moles per kilogram and then multiplying by kilogram to just get moles. And this equals 0.01275 moles per day. So to work out how many cans you can have in a day, we're going to do 0.01275 divided by 5.68 times 10 to the negative 4. And this equals 22.4 cans. But you can't have 0.4 of a can, so the number of cans that you can safely drink is 22. Because if you have 23 cans, that's going over 22.4 and therefore over the safe amount to drink in a day. To get the 3 marks for this question, you get a mark for working out the number of moles in 1 can, so 5.68 times 10 to the negative 4 moles. You get a mark for working out the number of moles you can have per day of aspartame, so 0.01275 moles. And then you get your third and final mark for working out how many cans you can have, so this is 22.4 or 22. The mark scheme will also accept 23, but it's better to put 22 or 22.4 because these are both within the limit and the actual safe amount that you can drink in a day. An organic compound I is analysed using a combination of techniques. The analytical data is shown below. Elemental analysis by mass, carbon is 56.69%, hydrogen 7.09%, nitrogen 11.02%, and oxygen is 25.20%. The mass spectrum molecular ion peak is at an MZ value of 127.0. We don't have the IR spectrum, but we do have the proton NMR spectrum. Part A. Explain the use of 2 deuterated compounds in NMR spectroscopy. The first use of a deuterated compound is as a solvent. Chloroform D, which is CdCl3, is a really common solvent in NMR spectroscopy. The second use of a deuterated compound is D2O, which is used to identify OH or NH peaks, because using D2O will get rid of these OH or NH peaks when they would be there if D2O wasn't present. To get the 2 marks for this question, you get a mark for talking about chloroform D being used as a solvent, and then you get a mark for D2O being used to identify OH or NH peaks. Part B. Determine the structure of compound I, showing all your reasoning. So the first thing to do when you get a question like this is to work out the empirical and the molecular formula. And we do this using the elemental analysis by mass. So starting with carbon, we do 56.69 divided by 12, and that equals 4.72. Then moving on to hydrogen, we have 7.09 divided by 1, which equals 7.09. Then nitrogen is 11.02 divided by 14, which equals 0.787. And finally, oxygen, 25.2 divided by 16 equals 1.575. Then we divide by the smallest number, which is nitrogen's 0.787. So dividing everything by 0.787, for nitrogen we get 1. For oxygen we're going to get 2, so dividing by 0.787 equals 2. For hydrogen, if we divide by 0.787, we get 9. And finally, carbon, dividing by 0.787, we get 6. So our empirical formula is C6H9NO2. Then we need to work out the molecular formula, and we do that using the molecular ion peak, which is going to be at 127. So that is the relative formula mass of our compound. So if we work out the relative formula mass of our empirical formula, we can either scale up or keep it the same. You can't scale down because empirical formula is the simplest way to write the molecular formula of a compound. So we do 12 times 6 plus 9 plus 14 plus 16 times 2, which equals 127.0. So we keep it the same. This is going to be our molecular formula and our empirical formula, which means that the molecular formula is the simplest way to write it. Then we're going to start looking at our spectrums. So we don't have the IR spectrum, but we do have the proton NMR spectrum. So this peak has a chemical shift value of 2.9 ppm, and it has a quartet splitting pattern also because there are 4 lines in the peak. But there's only 1 hydrogen in this environment. So 2.9 ppm is when you have a carbon double bond oxygen connected to a carbon with a hydrogen. So that's the chemical shift value for this specific group, which you can find out on your data sheet. But we want a quartet splitting pattern, so we want this hydrogen in the middle connected to CH3, because for each of these peaks, the carbon in question we're looking at is the middle one. So then moving on to when we have the first integration of 3. So this has a chemical shift value of 1.7 ppm, and it has a doublet splitting pattern because there's only 2 lines in this peak, and there are 3 hydrogens present. So this is the chemical shift value for when you have R and then CH. So it's just an alkyl group that the carbon hydrogen is connected to. So if we have CH and we want a doublet, but we have 3 hydrogens, so the hydrogens we're looking at are these 3, and by connecting it to a carbon with 1 hydrogen, that means we're going to produce a doublet splitting pattern. Finally, the last peak on the proton NMR also has an integration value of 3. It has a chemical shift value of 1.3 ppm, and it has a triplet splitting pattern, which means it will be connected to 2 hydrogens. And then finally there are 3 hydrogens because of the integration value of 3. So it's going to be CH3, CH2. And again, we're looking at this CH3 part because of the 3 hydrogens shown by the integration value, but we want a triplet splitting pattern, so we need to be next to 2 hydrogens, and because it's still in the range of RCH, so it's an alkyl group we're going to be connected to, we just need to have 2 hydrogens in our alkyl group, which is CH2. So we haven't yet thought about nitrogen. Looking at the proton NMR spectrum, we can see that there are no NH peaks, it's not in the NH range, and it's not in the amide range, which is C double bond O NH. So we know that the form our nitrogen is going to take is in a nitrile functional group, so C triple bonded to a nitrogen, because we can't also have another proton environment, we can't have any more hydrogens because we've only got these 4 environments shown in our NMR spectrum. So if we start by drawing our first structure, that is just going to be putting together all of these different groups that we've identified using the proton NMR spectrum. So we're going to have CH3, CH2, O, and then we're going to have C double bond oxygen, CH, CH3, and then this is the perfect place for our nitrile group to go, or our CN group. And then we can double check that we've got our 4 proton environments and they're all correct. So if we look at this first one here, we have got our first proton environment, our quartet splitting pattern with a chemical shift value of 4.2 because it's connected to this oxygen. Then if we move along and we look at this one, well, we have our proton environment here from our hydrogen. It's connected to this carbon double bond oxygen, and it will have a quartet splitting pattern because of this CH3 group. And then our 2 alkyl groups with the splitting patterns of 1.7 ppm and 1.3 ppm are shown because we have them here. That's our first one with a chemical shift value of 1.3 ppm, and then our second one with the CH3 is here in a kind of L shape at the end of our compound. So this is our first possible structure, but there's more than one answer for this question. So our next possible structure is CH3CH2O, so same to start with, but then we have our CH and CH3 group in the middle with our carbon double bond oxygen and our nitrile group at the end. So again, we are going to check our proton environments. So our 4.2 proton environment is shown here. This is going to be the hydrogen that creates this quartet. It's connected to a CH3, so it will have a quartet splitting pattern, and it's going to have a chemical shift value of 4.2 because of this oxygen that it's bonded to. Then if we look at our 2.9 ppm proton environment, so that's going to be this hydrogen here. Now it's still bonded to the carbon double bond oxygen. It's still going to be a quartet because of this CH3 group. So again, we've corrected and we've checked that we've got both proton environments. The 2 RCH groups, well, they are also represented. We have our first one here, and then we have our last one here where we have the CH3CH2, and then we have our CH3. So again, this is a very correct, another possible structure that we could have for this question. The last part of this question is to confirm the functional groups. So we have a carbonyl and a nitrile functional groups in our 2 compounds, and these are the 2 possible compound I's based on the data we've been given. Now, even though we don't have the IR spectrum, we were able to work backwards and find out that we need to have a carbonyl group to have the correct proton environment chemical shift value. And because if there was an NH something, so an amide or an amine, that would show up in the proton NMR spectrum. And there are only 4 proton environments, so we can't have an amine or an amide. We have to have this nitrile functional group. Because this is a level response question, there aren't specific marking points. Instead, to get the 6 marks, your structure of I has to have a viable chemical structure of C6H9NO2. So that's the molecular formula that we carried out. And it needs to have the key features which are consistent with the spectral data. So the carbonyl and the nitrile functional groups, and also making sure that your proton environments are correct and they match up with the spectra. Also, you need to have most of the data analysed.
So that works out because we don't have the IR spectrum, so we haven't been able to analyse the IR spectrum, but we have analysed every other bit of data, so that's most of the data analysed.